Welcome to Critical Reasons to Specify Insulating Glass. This course is brought to you by the National Glass Association and was created by the Glass Association of North America's Insulating Division in conjunction with its members. The National Glass Association is a registered provider with AIA. Following this presentation, you'll be directed to complete a brief quiz to ensure your understanding of the presentation's learning objectives. The ever-increasing demand for energy savings, building occupancy safety, and comfort have enabled the glass and glazing industry to bring many innovations to market. In this course, we'll look at the basics of insulating glass and discuss the key components and attributes associated with using insulating glass in buildings. Design considerations to address daylighting, acoustics, thermal performance, safety, and security will also be covered. By the end of this course, you'll be able to list the prime components of an insulating glass construction or assembly. Describe the purpose of a spacer in an insulating glass assembly. Discuss how insulating glass provides enhanced levels of security and safety performance. State 2 ways the acoustical performance of an insulating glass unit can be improved. Here's the description of this course. The demand for energy savings, building occupancy safety, and comfort have enabled the glass and glazing industry to bring many innovations to market. This course will cover the basic components of insulating glass and review some of the key performance attributes it provides. It shouldn't even be a question that a modern building include insulating glass of some type. The benefits far outweigh the slight cost difference to monolithic glass panels. The biggest reason to install insulating glass, or IG, is to control heat gain in the summer or heat loss in the winter. Daylighting from IG offsets the need for interior lighting. There are IG constructions that can withstand bomb blasts, hurricanes, burglars, and other hazards. Finally, IG cuts down the noise of the outside world, bringing peace and quiet and comfort to the occupants inside. Many options are available beyond just 2 pieces of glass used for IG, such as internal blinds, glass performance and color, and switchable shading. By the way, did you know it's always referred to as insulating glass and never as insulated glass? Here are 2 definitions of IG. In both cases, we have 2 pieces of glass, or lights, separated by a perimeter spacer, held together with sealants about the perimeter. The cavity between the glass lights is kept dry with a desiccating agent, lower conductivity gases, and so forth. Here we have a cutaway view of 3 window systems. The left has a single pane of glass. The middle has a typical 2-pane IG. The right-hand diagram shows a triple pane or tri-pane IG. The difference is that the thermal and acoustical performance is significantly enhanced as we move from left to right. This shows the primary components of an IG construction or assembly. Starting from the top, we see the 2 panes of glass, a cavity that holds dry air, noble gas, or blend of gases, the spacer which holds the glass apart, the desiccant which keeps the cavity space bone dry, and finally, the seal, which could be 1 or 2 different sealants that have different properties for diffusion control, moisture in or gas out, and structural strength. Here we show that a standard 2-pane IG has a single cavity, and a dual-pane IG has 2 cavities. Each must be kept bone dry to prevent condensation fogging associated with low temperatures. Here are some special IG constructions. The unit on the right has 4 panes of glass and performs very well in cold climates and noisy environments. The unit on the left has a plastic suspended film in the center to divide the cavity in 2. This provides thermal benefits. There are many different types of spacers designed for IG systems. The primary purpose is to hold the glass apart. The spacer also holds desiccant, which keeps the internal cavity very dry. Spacers also need to stick to sealants and keep them in place. Spacers help keep the moisture out and the gas fill in. The biggest component of IG is the glass, at least from an area perspective. There are many types and thicknesses of glass that get incorporated into an IG system based on energy performance, structural loads, building codes, and aesthetic requirements. The glass industry designates the surface of glass on the outermost part of the building as surface number 1. Each surface number designation then progresses upward until reaching the innermost surface inside the building. In the example shown, S number 1 is on the far left and S number 4 is on the far right. For instance, this is useful for describing high-performance coating locations of the assembly. The quad IG from slide 10 has 8 surfaces. Now let's talk about spacer system components. The purpose of a spacer is to act as a structural member to maintain airspace between glazing lights. It also is a carrier for the desiccant system and is a support system for sealants. Although there are other spacer systems available, the most common you'll see today are rigid or flexible systems. Rigid spacers have been the most common spacer system through the years, with the vast majority of that being extruded aluminum. These spacers are made into frames with the use of corner connecting keys, or are bent with equipment and connected with straight connectors. Over the decades, there have been many improvements to both spacer product offerings and fabrication equipment. As energy efficiency started to become a higher priority, new spacer systems were made to increase the thermal efficiency of IGs. The first changes dealt with changing from an extruded aluminum to a roll-formed aluminum in a U-shape to cut out the conduction path across the roof of the traditional aluminum spacer. By removing the roof of the spacer, it created a longer path for the thermal energy to transfer from one pane of glass to the other, which increased the thermal efficiency of the IG unit. There were also changes to the material of the spacers. Instead of using aluminum, which is very conductive, the material was changed to stainless steel that transfers energy at a much lower rate. And as requirements accelerated beyond that, plastic was introduced, which is far less conductive than both aluminum and stainless steel. Most of these new spacers with plastic were hybrids and still use aluminum or stainless steel to keep the benefits of having the inorganic surface aluminum and stainless steel provided, but used plastics to cut down the paths of energy transfer even further. Flexible spacers were also introduced as the efficiency of windows became more important. Flexible spacers incorporated rubbers and plastics for their low conductivity numbers. They typically include reinforcing rigid materials to maintain their structure. These spacers are typically applied to glass with automated systems or special applicators, and are not bent like traditional rigid spacers. Desiccant is used in all spacer systems. Typically with rigid spacers, it's filled with beta desiccants, but there are some that use a desiccating matrix that is applied during the construction of the frames. With flexible systems, the desiccant is usually integrated into the spacer at the spacer's production. The two basic spacer sealant systems are single and dual sealed units. Typically, single seal units are not very large, and because they don't require high structural strength, will only use one sealant in their IG. It's important in these units that the sealant used needs to have low gas and moisture transmission rates, but still enough structural integrity to keep the IG unit together. Dual seal is typically required when the structural integrity is much more important. In commercial buildings, almost all units are dual seal. They use the primary seal that has low gas and moisture transmission rates, but due to the lack of structural integrity in these seals, will use a secondary seal that will provide that. In both these units, the spacer needs to have the ability to resist the moisture and vapor penetration as well. In dual seal units especially, since the sealant used has a high transmission rate. All IG units need to be sealed to keep the integrity of the units. There are many different types of sealants that can be used, and the ones listed are not the only ones on the market. All IG units, however, require a primary seal for the purpose of keeping the interior airspace of the IG free from moisture and gas penetration. Typical primary seals have low transmission rates, which keep the moisture and gas out, but aren't usually strong enough for structural applications. When there is a need for structural integrity, a different secondary seal is required. These secondary sealants are significantly stronger for keeping the glass panes and spacers together, even in large units that have little additional support. They are very porous, however, and allow gas and moisture to pass through them fairly easily. We've all seen failed IG units that contain significant condensation inside the airspace. Desiccant is used in IG units to absorb the moisture that is in the IG during construction, while the sealants keep any moisture out of the airspace. Some desiccants can also absorb volatiles that can stick to coatings, causing discoloration. It's very important to ensure there is sufficient desiccant inside the IG unit, or premature failures will occur. The energy will always flow from hot to cold by either conduction, convection, or radiation. Most of the energy is transmitted by conduction through the frame. Convection is the heat transfer from movements of fluid. This can happen naturally as hot air rises and cool air sinks, or through forced air from wind and mechanical air movement, such as from HVAC systems. This convection happens inside a building's airspace, outside of the building, and between the lights of glass in the IG airspace. Because of this convection in the airspace, the distance between the lights of glass should always be taken into consideration. If it's too large, there will be an increase in convection energy transfer that can affect the efficiency of the IG. Radiation is the energy that is transmitted through space in the form of waves or particles. All objects radiate heat in the form of short or long-wave radiation. The hotter the object, the shorter wavelength radiation. The sun is the major form of short-wave radiation. The long-wave radiation comes from other objects in the surroundings. There are many improvements to improve thermal performance of windows. Monolithic or single lights of glass without coatings were used in the past commonly and are still being used, mostly in warmer climates. These windows provide minimal resistance to radiant and conductive energy transfer. By adding a second light of glass creating an airspace, you break up the conduction to just the edge of the glass, significantly reducing the path for energy to be transferred. Low emissivity coatings are used to limit radiant heat energy that pass through the glass. A thin coating on the surface of the glass is used to reflect infrared light or heat energy while still letting visible light through the glass. Different coatings will be used in different climates to get the desired effect. To increase the IG efficiency after adding lights of glass and coating, using warm edge spacer systems and substituting air with other less conductive inert gases such as argon or krypton can be incorporated. The main measurement of IG and window performance or thermal transmittance used today is the U factor. This measures the air-to-air heat transmission due to the difference in indoor and outdoor temperatures and incident radiation. This measurement takes into account all three modes of heat transfer. The lower the U factor, the less heat that can transfer through the IG. Sometimes R values will be used instead of U factors, and this is just the inverse of the U factor. The higher the R value, the more efficient the IG is. Solar heat gain coefficient, or SHGC, is an important factor in performance. Solar heat gain coefficient is the ratio of the solar heat gain entering the space area through the fenestration product to the incident solar radiation. Solar heat gain includes directly transmitted solar heat and absorbed solar radiation, which is then re-radiated, conducted, or convected into the interior. The value of SHGC is from 0 to 1. The lower the SHGC, the less solar heat gets transmitted through the window. Some examples would be a double-glazed IG with low E coatings blocking a lot of the infrared transmission having an SHGC of 0.39, while a clear single light of glass has around a 0.86 SHGC. In some climates, a higher SHGC is desired to help heat a space, but it's a delicate balance in most locations. If the SHGC is high to help heat in the winter, it could be a problem with overheating in the summer. Visible light transmittance, or VLT, is the amount of light in the visible portion of the spectrum, 390 to 780 nanometers, that passes through a glazing material. A higher VLT means there is more daylight in a space. Note that edge of glass and framing are not included in this measurement. Visible light transmittance is influenced by the glazing type, the number of panes, and any glass coatings. Visible light transmittance of glazing ranges from above 90% for typical uncoated low-iron glass to less than 10% for highly reflective coatings on tinted glass. A typical double-pane IGU had a VLT of around 78%. This value decreases somewhat by adding a low-E coating and decreased substantially when adding a tint. This image shows us the impact of light transmission. As noted earlier, visible light transmission varies based on glass type, coatings, and films. The lower the VT, the less light is let through. Insulating glass can also include components that provide dynamic solar control. These may include conventional dynamic solar shading systems, such as roller shades or blinds, or can involve operation of a glazing layer with a reversible optical switch from high to low transmission. Some of the more common technologies include electrochromic, which reacts to electrical charge. This application requires wiring. Photochromic, which reacts to sunlight intensity, and thermochromic, which reacts to glass temperature. One of the significant advantages of dynamic glazing is the ability to change the glazing properties based on environmental conditions outside. These photos demonstrate capabilities of dynamic glazing to adjust visible light transmission, or glare, to provide optimal daylighting conditions. In the photo on the left, the dynamic glazing is highly transparent on a cloudy day, while the photo on the right, the same glazing is tinted on a bright sunny day to minimize glare and control solar heat gain. These photos are courtesy of Sage Electrochromics. The formation of condensation on the interior glazing surface can also be addressed with insulating glass. Condensation resistance is a measure of a fenestration system's ability to resist the formation of moisture condensation on interior surfaces, whether physically measured or computer simulated. AMA uses a rating called Condensation Resistance Factor, or CRF. The AMA rating is based on a dimensionless scale, generally in the range of 0 to 100, with a higher number representing a greater resistance to condensation formation. NFRC also has a rating system called Condensation Resistance. NFRC condensation resistance is based on a dimensionless scale of 1 to 100, with a higher number representing a greater resistance to condensation formation. Condensation resistance is typically a localized effect due to thermal conductivity differences of discrete components. A highly conductive material that reaches from the warm side surface to the cold side surface will create a localized heat flux, significantly greater than the lower conductivity insulating materials around it, creating a thermal short circuit. Such thermal short circuits can have a detrimental effect on the ability of a fenestration system to resist moisture condensation. Here's an example of a unit with considerable condensation. In some cases, the impact of such condensation can be so severe that frost and/or ice can form on the interior surfaces of the window. This can lead to a variety of problems, including water damage and poor indoor air quality. Efforts to improve fenestration system performance to improve condensation resistance include optimization of framing materials and thermal breaks, control of air leakage through weather seals and frame joints, and the optimization of the insulating glass unit component. A second purpose for using insulating glass is improving safety and security. Modern architectural designs often require glazing materials that provide enhanced levels of security and safety performance properties. Laminated insulating glass is used to meet these design requirements. Laminated glazing materials consist of multiple plies of glass, interlayers, resins, and/or plastic glazing materials bonded together under heat and pressure. This graphic shows a typical laminated IG construction. Laminated glass's most important characteristic is the ability of the interlayer to support and hold the glass when broken, and/or plastic sheet when cracked. This provides for increased protection against fallout and penetration of the opening. Most building codes require the use of laminated glass for overhead glazing as monolithic lights, or as the lower light in multiple glazed units. Other applications include safety, security, detention, seismic resistant, blast resistant, bullet resistant, burglary resistant, hurricane cyclic wind resistant, and sound reduction applications. Laminated glazing materials are also used in specialty applications such as aquariums, animal enclosures, glass stairs, floors, and sports stadiums. The laminated glass can also be insulated to provide the added benefit of solar control and thermal performance. There are many configurations for laminated glass depending on the level and type of protective glazing. Consult your IG fabricator for specific glazing options that are available. Note: the Ghana Glazing Manual and Laminated Glazing Reference Manual should be consulted for additional detailed information on laminated glass, burglar-resistant, bullet-resistant, and physical attack-resistant laminated constructions prior to specifying and using laminated glass constructions. For windows, doors, and curtain wall systems designed for use in hurricane or high-velocity wind zones, third-party testing is done to simulate windborne debris striking a window during a hurricane. This is a two-part test. Part 1. In a controlled laboratory setting, a 2x4 projectile or 2-gram steel shot balls, depending on required protection level, are fired at predetermined locations on the window and seeing if there is any penetration. Part 2. The cycling portion of the testing is then conducted on the same test window to ensure that a window having withstood impact by the 2x4 can then stand up to rapid increases and decreases in pressure within the building during a hurricane. Within the laboratory setting, this is done by introducing 9,000 cycles of differing pressures to the impacted unit. Common test methods and standards surrounding hurricane testing are State of Florida TAS 201, 202, and 203, ASTM E1886 and E1996, AMA 506, Miami-Dade County testing protocols, etc. Acoustical performance of an insulating glass unit can be improved by increasing the mass of the unit by using thicker glass. This obviously makes for a heavier unit. Increasing the spacer between the lights of glass. Unfortunately, significant increases are required to have a substantive improvement. Using laminated glass, particularly those with an acoustic interlayer. Use of a flexible spacer system to help reduce sound transmission, or any combination of the above. STC and OITC are completely different rating systems that result in different values and cannot be compared to each other. STC was originally developed for rating the acoustical performance of interior partitions, as at the time there was no method for rating the acoustical performance of building envelope components. STC was used for this too. Unfortunately, it took quite a few years for the OITC system to be developed, and by the time it was introduced, STC was used throughout the building component industry, even though it was not intended for this purpose. That's why STC is so frequently referenced for windows, doors, etc. OITC is gaining slow acceptance as a replacement. As noted before, relying solely on mass and glazing space to improve acoustical performance results in a big, heavy unit. By having interior and exterior lights of different types and/or thickness, sound transmission from one light to the other is reduced, as each light has different resonant frequencies. Acoustical interlayers absorb a range of sound frequencies to prevent transmission to the interior light. This also acts to decouple the system when used with a monolithic interior light. Other available features include translucent or diffused light panels that allow light to penetrate but not visible images, components between the glass including grids or blinds, ranges of glass colors, and completely opaque spandrel panels used in curtain wall systems to block the visibility of floor slab edges. Glass Magazine is NGA's official publication. There are many other organizations that touch on various aspects of the construction and glass industry, several of which are provided here as well. Technology plays a large role in what our companies do each day. Here are a few software resources that you should consider looking at when evaluating a project that includes glass and glazing components. Some information for this presentation was gained through the Insulating Glass Manufacturers Alliance and the American Architectural Manufacturers Association. Throughout this course, we've talked about various aspects of insulating glass. You now have the ability to list the primary components of an insulating glass construction or assembly. Describe the purpose of a spacer in an insulating glass assembly. Discuss how insulating glass provides enhanced levels of security and safety performance. And state 2 ways the acoustical performance of an insulating glass unit can be improved. Thank you again for attending Critical Reasons to Specify Insulating Glass. We hope this continuing education program was helpful in bringing you up to date on the capabilities of insulating glass materials that are currently available. Please click Next to be taken to the questionnaire, which will allow you to complete this course.